So let us discuss about materials known as dielectrics. What are dielectrics? Dielectrics are insulators. Dielectrics are insulators and they are used to store electric energy or electrostatic energy. Okay. And there are two types of dielectrics. First type is polar dielectrics and second type is non-polar dielectrics. Okay. So what are polar dielectrics and what are non-polar dielectrics? So see, we have molecules such as HCl. Okay, this is HCl molecule. So which is actually H positive and Cl negative ions connected by means of an ionic bond. Okay, so this is a positive charge separated from a negative charge, same amount of negative charge by some distance. Okay, so this is like a dipole. This is like an electric dipole, right? So it will have some dipole moment. These kinds of molecules which have intrinsic dipole moments, they are known as polar dielectrics. Okay, so here by definition, the center of positive charge and center of negative charge, they are separated from each other. Okay, this is positive charge, this is negative charge. So center of mass of positive charge and center of mass of negative charge, they are separated from each other. So this kind of molecule, it is known as a polar molecule. Okay, so examples are HCl, then H2O, this is another example. So they will have some intrinsic dipole moment. Then most of the other molecules, they don't possess this intrinsic dipole moment. They are known as non-polar molecules. Okay, so for an example, H2, okay, CO2, these kind of molecules, they don't possess intrinsic dipole moment. Okay, so here center of mass of positive and negative charges, they are coinciding. So there is no separation between the center of mass of positive and negative charges. So they are known as non-polar molecules. So these are some examples of polar molecules: HCl, water, that is H2O, alcohol, NH3, etc. etc. These are polar molecules and these are non-polar molecules. Okay, or polar dielectrics we can say, and non-polar dielectrics. So is it clear? Yes, no? Then now let's suppose we keep a dielectric in an external electric field. Okay, so what is the effect of external electric field on a dielectric? So first of all, let's consider a polar dielectric. So let's suppose this polar dielectric is kept in some external electric field. What will happen? Okay, so initially, suppose the electric field is 0. Okay, so on this side the electric field is 0. Okay, so in this sample we have polar dielectric. These are various molecules of polar dielectric. Now, if external electric field is 0, the dipole moments of individual molecules, they will be aligned in different directions. Okay, what is direction of dipole moment of a dipole? It is directed from negative to positive, right? So for this molecule, it is directed like this. This is p bar. For this molecule, it is directed like this. Okay, for this molecule it is directed like this, from minus q to plus q. Okay, for this one it is directed like this. So for all individual molecules, their dipole moments are directed in various directions. Okay, and therefore the net dipole moment of material is 0. Net dipole moment of a dielectric is 0. Okay, in absence of an external electric field. So if external electric field is 0, the net dipole moment would be 0, right? Now what happens if we have external electric field? So suppose we have external electric field which is directed like this, so we know the effect of external electric field on a dipole. What does the external electric field do on dipole? It exerts a torque, right? And due to that torque, the dipoles will get rotated. So these individual molecules, they get rotated. Okay, so in polar dielectric, all molecules, they have their original dipole moment, intrinsic dipole moment, and intrinsic means of their own. Okay, and when you apply an external electric field, the dipole moments which were aligned in various possible directions, they get aligned in the direction of the external electric field. Okay, and the material now gains some dipole moment along the external electric field. Okay, material gains some dipole moment along the external electric field, and this phenomena is known as polarization. This is known as what? Polarization. Okay, and this polarization happens mainly because of rotation of individual dipole moments. Okay, so this is for the polar dielectric. Then let's think of then let's think of non-polar dielectric. What happens in case of a non-polar dielectric? So we know what is non-polar dielectric. So for each molecule of a non-polar dielectric, the center of mass of positive charge and center of mass of negative charge, they are coinciding. There is no separation. There is no there is no intrinsic dipole moment. But then when you apply an external electric field, what will happen? So see here, positive and negative charge, you can say they are coinciding. Okay, the center of masses are coinciding. Okay, all right. So if you apply an external electric field, what happens? So suppose electric field is in this direction, like this. So what happens is the negative charge gets attracted by the electric field, you can say, and the positive charge, it gets pushed in direction of the external electric field. Okay, negative charge gets attracted, positive charge gets pushed in the direction of external electric field, and that's why the center of mass of the positive and negative charges, they get separated. The center of masses of positive and negative charges get separated, and because of that, what happens now? So initially there was no dipole moment for each molecule. Now each molecule will have some dipole moment because of separation of positive and negative charges. Okay, so this is another type of polarization. This happens because of separation of center of masses of positive and negative charges, and this happens in case of non-polar dielectrics. Okay, so initially there was no dipole moment. Now some dipole moment is induced if external electric field is non-zero. Okay, right? So in nutshell, if you have polar dielectric, okay, so in absence of external electric field, there will not be any net dipole moment, right? Because dipoles of individual molecules, they are directed in various possible directions. Okay, but when you apply external electric field, what happens? It gains some net dipole moment because all dipoles, they get aligned in the direction of external electric field. And in case of non-polar dielectric, what happens? The molecules, they don't possess any intrinsic dipole moment, but when you apply an external electric field, the center of mass of positive and negative charges, they get separated. So dipole moment is generated. It gets induced. Okay. So again, the material will possess now some net dipole moment in direction of electric field. Okay, so this act is known as was polarization. Okay, induction of the dipole moment, net dipole moment. Okay, it is known as polarization, right? So let's define polarization. What is polarization? So the net dipole moment per unit volume is called polarization. Okay, so let's suppose dipole moment of each individual molecule is suppose small p. Then there are n such molecules in volume V. So total dipole moment will be equal to n times p. Okay, n times the small p bar. And if you divide that by volume, okay, then this term is known as polarization. The net dipole moment per unit volume. Okay. So where n is what? Number of molecules, p bar, small p bar is dipole moment of individual dipoles, and v is the volume, right? So now this polarization, it happens because of what? It happens because of the external electric field. Okay, polarization happens because of the external electric field. That means it will be directly proportional to the external electric field. Okay, more is the electric field, more polarization will be there. Okay, so polarization is directly proportional to external electric field. Okay, and if you remove this proportionality sign and put an equality sign, there will be a constant. This constant is known as susceptibility of a material, electric susceptibility of a material, right? So is it clear? So till now we have studied capacitance with air, right? Till now we have studied only air-filled capacitors. So the medium between two plates of a parallel plate capacitor is air, was air, right? Now we'll consider some dielectric, meaning some insulator is inserted in between the two plates of a capacitor. Okay, so what happens if dielectric is inserted between two plates of a capacitor? So we know that, see, we have just seen that if dielectric is kept in external electric field, it gets polarized. Okay, it gets polarized. So suppose we have this slab of dielectric. Okay, so initially it might be polar, it might be non-polar dielectric. So we apply some external electric field. Some external electric field is applied like this. Okay, so what happens because of this external electric field? There is some polarization. Okay, so see, the negative charge will get attracted towards, we can say, this side, and positive charge will be pushed by electric field. Negative charge will be attracted. Okay, so the charges, there is separation between charges, or if you have original dipoles, okay, intrinsic dipoles, they get aligned in the direction of the external electric field like this. So there will be millions of molecules. I have drawn just a few of molecules. So see what will happen. So if you think about this side of this cube of dielectric, it will gain net negative charge, right? Okay, this space will gain net negative charge. See, okay, and this space will gain net positive charge. Okay, and if you think of all other charges, okay, so for every positive charge there will be a negative charge. Okay, for every positive charge there is a negative charge. So the net charge inside, you can say, it's equal to 0. But this side and this side will have some negative charge on this side, and there will be some positive charge on this side. Okay, so it is like, now it's like negatively charged surface on this side and positively charged surface on this side, and net charge inside is 0. Okay, so now what will happen? So you have some external electric field like this. You have some external electric field. Sorry. Oh, there is some external electric field in this direction. Okay, and there will be an induced electric field. Okay, there is an induced electric field inside the dielectric. And what will be the direction of that induced electric field? So induced electric field is because of polarization of this dielectric, right? because now dipole moments are created, dipole moments are induced. Okay, this is polarized. That's why we have net negative charge on this side, net positive charge on the other side. So the electric field due to polarization will be directed like this. Okay, from this positive to this negative phase, right? So outside of this dielectric, the electric field is E bar. But inside this dielectric, the electric field is this E bar minus electric field due to polarization. We can say EP bar. Okay, inside this dielectric, the electric field is E bar minus EP bar. Got it? So net electric field inside this dielectric will be lesser than the applied electric field. Got it? Yes, no? Okay. Net electric field inside the dielectric will be less than the applied electric field. Okay. So now therefore, see, now let's consider a capacitor. Okay, let's consider a capacitor like this. So the distance between two plates of a capacitor is D, suppose. Okay, distance between these two plates is D. Then we have inserted a dielectric in between. So positive plate, I mean the capacitor is charged to the charge Q, charge equal to Q, and because of this thing, okay, because of this dielectric now, what will happen? I mean, when dielectric is kept inside this capacitor, it will get polarized as we have just seen. Okay, some positive charge gets developed on this side, some negative charge gets developed on the other side. Okay, so some negative charge gets developed on this side of a dielectric, some positive charge gets developed on this side. So inside the capacitor but outside of the dielectric, how much would be the electric field? We know, we have studied the electric field inside a capacitor. It is sigma divided by epsilon naught, right? So electric field in the region, okay, without dielectric, I can say without dielectric, suppose E bar, which is sigma divided by epsilon naught, or let's call it E naught. Okay, E naught bar, its original electric field in absence of dielectric. Okay, and it's directed along x cap, or let's consider the magnitude only. Okay, so E is equal to what? Sigma divided by E naught is equal to sigma divided by epsilon naught. Now here what happens is, okay, inside the dielectric, if you consider this space, okay, electric field will be less. Okay, I mean inside the dielectric, the electric field will be less than outside the dielectric. How much will that be? So to find out electric field, we need to find out the surface charge on the dielectric. So how much is surface charge? So suppose because of polarization, surface charge QP gets developed. Okay, suppose QP is the surface charge on dielectric, and it's because of due to polarization. It is surface charge on dielectric because of polarization, and there is this surface charge. Okay, so we can say the surface charge density, surface charge inside the dielectric is, uh, I'm sorry, if you think of this space, the surface charge would be how much? It is Q minus QP, because, okay, see, there is plus Q charge which you have applied to this plate, and there is minus QP charge developed on this face of the dielectric. Okay, so you can think like this: if this plate of capacitor and this face of dielectric, they are in contact, how much would be the net surface charge? It will be Q minus QP. because here we have negative charge developed. Okay, so I can say therefore, okay, net surface charge on dielectric is equal to, it is equal to what? Q minus Qp. So surface charge density, okay, so surface charge density we can say is, you can divide this charge by area. Okay, so let's call it sigma dash, so it will be Q minus Qp divided by area. Okay, and this sigma dash is equal to, I can say, Q upon A minus Qp upon A. Okay, so what is Q upon A? It is sigma, right? Q upon A, this is Q divided by area is sigma, surface charge density of the capacitor. And let's call Qp divided by A as surface charge density due to charge due to polarization. Okay, so I can say it is sigma minus sigma p, where sigma p is, okay, where sigma p is surface charge density due to what? Due to polarization. Okay, so is it clear till this point? All right. So this is surface charge density due to polarization. Now this surface charge density will be directly proportional to the external electric field. Okay, so can I say sigma p will be directly proportional to the external electric field? What is external electric field? It's E naught. Okay, because if you apply more field, more polarization will be there. If there is more polarization, more surface charge will be there. So this is directly proportional to the external electric field. Okay, but we know what is external electric field, and E naught is just equal to sigma divided by epsilon naught. Okay, so I can say sigma or E naught is proportional to sigma, or in other way we can say sigma is proportional to E naught, right? It is proportional to E naught. So see, sigma p is proportional to E naught, I can say, and E naught is proportional to sigma. Okay, so we can say that therefore sigma p is proportional to sigma. This thing we can say, right? There is no problem. Then I want to find out actually what is sigma minus sigma p. So can I say sigma minus sigma p is also proportional to sigma, because sigma p is proportional to sigma. Okay, so minus sigma p is also proportional to sigma, right? Just proportionality constant will be negative. Okay, and if you add another sigma to that, what will happen? If you just add another sigma to that, on right hand side you will have to add sigma. Okay, so instead of, right, this sigma you will have, okay, some proportionality constant times sigma plus sigma. Okay, so anyways it will be proportional to sigma only. Are you getting this? See, sigma p is proportional to sigma. Why? Because surface charge density is proportional to the external electric field, and external electric field can be written as sigma upon epsilon naught. Okay, where epsilon naught is a constant, so external electric field is proportional to sigma. That means you can write, since this is proportional to sigma, you can write sigma p is proportional to sigma. Okay, right? Then I can also say that minus sigma p is also proportional to sigma. Just proportionality constant will be negative. Okay, minus sigma p is also proportional to sigma. Okay, and then if I add sigma on both sides, so still this term will be proportional to sigma because I am just adding sigma on both sides. Got it? Yes, no? Then here we write the proportionality constant between this thing and this thing as k. Okay, sigma minus sigma p is equal to, we write sigma divided by k. Okay, we write it as sigma divided by k. Okay, because this thing will be less than sigma. Okay, this term will be less than sigma, so we divide sigma by k. Okay, so this is our proportionality constant, and this is different for different dielectrics. So k is known as a dielectric constant, because how much of polarization will be produced in a dielectric, it depends on the properties of dielectric, right? Sigma p, the surface charge density due to polarization, it depends on properties of dielectric. For same electric field, different dielectrics will respond in a different way. Okay, and therefore what we can say is, now therefore the electric field inside a dielectric, we can say it is E dash, and E dash is equal to what? E dash is equal to, we can say, sigma dash divided by epsilon naught. Okay, so electric field is sigma upon epsilon naught. What is resultant surface charge density in a dielectric? It is sigma dash, which is sigma minus sigma p. So we can say the electric field there will be sigma dash divided by epsilon naught. And what is sigma dash? It is sigma minus sigma p, which is equal to sigma divided by k. Okay, so we can say that electric field inside dielectric, E dash will be equal to what? It will be sigma upon epsilon 0 k. Or you can say it is the applied electric field or electric field inside the capacitor in the region where no dielectric is present. Okay, so E dash is equal to E divided by k. Sorry, E naught divided by k. Okay, because E naught is what? Sigma upon epsilon naught. Right. So this is the formula for resultant electric field inside the dielectric. But we wanted to find out the effect of dielectric on capacitance. Okay, and we just found out the effect of dielectric on the electric field. We just found out electric field inside the dielectric, right? So now, how is this relevant? So see, let's consider that capacitor again. So this is, sorry, this is our capacitor, and it is filled with a dielectric. There is this dielectric inside the capacitor. Okay, so there is charge on capacitor, suppose plus q and minus q. Okay, and distance between these two plates is d, and thickness of dielectric is t. So can I say in this region the electric field is sigma divided by epsilon naught? What is sigma? Sigma is q upon this surface area of the plate. Okay, so electric field in the region without dielectric okay is E naught, which is sigma divided by epsilon naught. Okay, and electric field in the region of dielectric, in the region of dielectric, you can say it is E dash, which is equal to sigma divided by epsilon 0 k, or you can say it is E naught divided by k. Okay, this is what we found out. Then how do we define the capacitance? So capacitance is defined by C is equal to what? Charge divided by potential difference. Okay, C is equal to Q upon V. And what is potential difference? What is potential difference in terms of electric field? We know E is equal to V upon D, right? If electric field is constant, it is just potential difference divided by distance. Okay, so I can say that, okay, see, for this much distance, potential difference between these 2 points, you can say, okay, potential difference between, let's draw some points, let's consider some points. So let's call these points as A, B, C and D. So I want to find out potential difference between points A and D, because these are points on two plates of the capacitor. Okay, so here the potential difference between these 2 points B and C will be how much? It will be the electric field inside the dielectric, which is E dash, E dash multiplied by this thickness. Okay, so I can say that electric field E dash is equal to potential difference between these 2 points B and C. Okay, it is equal to VBC divided by distance between these 2 points. So distance is T. So VBC divided by T, and which implies VBC is equal to what? VBC is equal to E dash multiplied by T. Okay, then now this much distance would be something, you can call it D1. This much distance would be something, D2 you can say. Okay, so how much would be potential difference between A and B? So it is, let's call this distance D1, this distance is D2. Okay, potential difference between A and B will be equal to the electric, similar way, in similar way, electric field here multiplied by this distance. Okay, so E times D1. Potential difference between C and D, so VCD you can say, it is equal to E times D2, right? So now I can find out potential difference between points A and D. So it is this much potential difference plus this much potential difference plus this much potential difference, right? So let's add a page here. So I can say potential difference between points A and B, because I want to find out potential difference between two plates of the capacitor where dielectric is inserted, right? So potential difference between these two plates, okay, it will be equal to potential difference from A to B plus potential difference from B to C plus potential difference from C to D. Okay, so it is VA, which point V, okay, sorry, I wanted to find potential difference between A and D, right? This point is A, this is D, so it's not AB, it is AD. So it is VAB plus VBC plus VCD, right? That is equal to, what is VAB? It is E times D1. Electric field here is E, or we called it E naught, sorry, we called it E naught. Electric field is E naught. Okay, so E naught times D1. Here it is E dash times T, and here it is E naught times D2. So thickness of dielectric is D, right? So it is equal to E naught times D1, okay, plus VBC is E dash times thickness of dielectric is T, plus we have E naught times D2. Okay, E naught we can take common, so it is E naught times D1 plus D2 plus what is E dash? E dash is E naught divided by, it is E naught divided by K. Okay, so it is E naught divided by K multiplied by T, right? Then what is D1 plus D2? So the distance between two plates of capacitor is D. The distance between two surfaces of dielectric is T. So the remaining distance is D1 and D2, D1 plus D2. So I can say remaining distance is this complete distance minus T. Okay. So I can say it is E naught times complete distance, which is D, minus T, plus we have E naught times T divided by K. This is VAD, right? So then I can take E naught common from all of this. Okay. Just let me know if you don't understand something. So I can take E naught common. What do I get? I get D minus T plus T by K. Okay. And what is E naught? So E naught is sigma divided by epsilon naught. Okay, this is VAD. This is sigma divided by epsilon naught, and it is D minus T plus T divided by K. K is the dielectric constant, right? And then what is sigma? It is Q upon A, charge on capacitor, divided by area. And then I want capacitance. I want capacitance, which is Q upon potential difference, Q divided by VAD. Okay, which is, if you take VAD on other side, okay, this is VAD, right? If you take it on other side, it goes to the denominator, and then you can take all other things on left hand side. So you get C equals to, okay, Q upon VAD, which is epsilon naught A divided by, you have D minus T plus T by K. This is a general formula. So if you insert dielectric plate, sorry, if you insert a dielectric plate between two terminals of capacitor, again sorry, if you insert a dielectric plate in between two plates of capacitor, okay, and thickness of that dielectric plate is T, then what will be the effect on capacitance? So in general, you get this formula: C is equal to epsilon naught A divided by D minus T. So total distance is D minus this distance plus T divided by K. This is the formula. Okay, T divided by K. Okay, so this is the general formula, and there can be a question on this. Okay, so possibility cannot be ruled out. Then now we'll see a specific case. So specific cases, T is equal to D. Okay, so what will happen? So put T equals to D. So this thing will become 0, and this thing becomes D upon K. So we get capacitance C dash is equal to, okay, so C is equal to epsilon naught A divided by D by K. Okay, so you can take that K in the numerator. So you get C dash equals to epsilon naught K A divided by D, right? Epsilon naught K A divided by D. So without the dielectric, capacitance without dielectric, capacitance of air-filled capacitor. Air-filled capacitor is, suppose C air, it's equal to epsilon naught A divided by D. So what is the difference between air-filled capacitor and capacitor with dielectric, some other insulator whose dielectric constant is K? So you just have to multiply this capacitance by K, the dielectric constant. That's it. Okay, so C dash is equal to what? C of a dielectric, capacitor filled with dielectric, is K times C air. Okay, so this is the effect. Alright, so this was special case. Let's call it special case number 1, that capacitor is completely filled by a dielectric. Okay, so total space between the two plates of capacitor is filled with a dielectric. Let's consider special case number 2. So here you can see these are two plates of a capacitor. Okay, this charge is plus Q, this is minus Q, and there is different dielectrics, okay, are filled within these plates, but in a definite fashion. Okay, what is that definite fashion? So see, this dielectric, whose dielectric constant is K1, it is filled like this. Okay, so there are various plates of various dielectrics having dielectric constants K1, K2, K3, so on and so forth. Okay, so they are kept like this. Those plates are kept like this. Okay, so plates will be, the dielectric plates will be parallel to each other, but the capacitance due to these plates, so if you consider this dielectric, okay, so this capacitor and this capacitor, they are in series combination. Okay, so capacitance in this dielectric plate and capacitance in this dielectric plate, they are in series combination. You can see that in series combination, if you take series combination of two capacitors, so one plate is in contact, right? This is C1, this is C2. So one plate of these two capacitors, it is in contact. The other plates, they are connected to either other capacitor or some other device or a battery. So here also you can say one side of these two dielectrics, okay, dielectric plates, one side is in contact and the other side, it is connected to what? Something else. Okay, other side is connected to not the same capacitor, okay, it is connected to something else. So other side of this one is connected to something else, other side of this one is connected to something else, either a device or a battery. So this is series combination. Got it? Yes, no? Okay, and then therefore what will be the resultant capacitance? So resultant capacitance will be capacitance of this one plus capacitance, sorry, it is series combination of capacitors. So reciprocal of the resultant capacitance is 1 upon Cs. It's equal to 1 upon C1 plus 1 upon C2 plus so on and so forth up to 1 upon Cn. Right? And what will be C1, C2, etc.? So we can find out that. So see, so in this case, now we can find out C1, C2, etc. So this is suppose D1. This much distance is D1. This much distance is D2. Okay, so this is like a capacitor whose area of plate is A. Okay, distance between two plates is D1. So how much would be C1? C1 is equal to epsilon naught K1A divided by D, right? C2 is equal to epsilon naught K2A divided by D. But see, D is equal to what? It's not total distance between the two plates of capacitor. It is this much distance only. Okay, thickness of the plate, thickness of the dielectric plate. Okay, so it is D1, this will be D2, C3 will be epsilon naught K3A divided by D3. Okay, So if there is such a problem, what we have to do is we have to find out C1, C2, C3, etc., etc., and then the net capacitance 1 upon Cs would be equal to what? 1 upon C1 plus 1 upon C2 plus so on and so forth up to plus 1 upon Cs. Got it? Next is case number 3. So here you have two plates of a capacitor, and the dielectrics are, they are inserted. This is K1. Okay, dielectrics are inserted like this, right? So one dielectric is filled in total space between the two plates, but not in complete area. In some area, one dielectric is inserted. In some other area, another dielectric is inserted. In this area A3, this another dielectric is inserted. In this area A4, another dielectric is inserted, right? So this is parallel combination. Okay, this is a parallel combination. How is this a parallel combination? See, in parallel combination, what do we have? The plates of capacitors. Okay, both the plates, they are connected, right? C1 and C2. They are in parallel combination. Then both the plates are connected to each other. So here also you can see these are the plates of these dielectric field capacitors. Okay, so this will be one capacitor, this will be second capacitor, this will be the third capacitor, this one will be the fourth capacitor, etc., etc. So these plates, there is a contact, right? This is the contact point. This plate and this plate, they are connected at this point. This plate and this plate, they are connected at this point. So both the plates are connected to each other. So this is a parallel combination. So here also this plate and this plate, they are connected to each other. This plate and this plate, they are connected to each other. So both the plates are connected to each other. So this is also a parallel combination. Got it? So in parallel combination, what is the total capacitance? What is the net capacitance? So just find out the equivalent capacitance of this one, this one, this one, this one, etc., etc. Net capacitance would be just sum of all those capacitances. Okay. So C1 is equal to, sorry, C is equal to the total capacitance. Okay, let's call it Cp. So this C1, or it is for this capacitor, right? So for this capacitor, which is filled with various dielectrics, the net capacitance is just capacitance of this one plus capacitance of this one plus capacitance of this one plus capacitance of this one, so on and so forth. Okay. And how to find capacitances of these individual capacitors? So it is epsilon naught k into A divided by D. So D is same, right? D is same for all. Distance between the two plates is same. What is different? Area is different. Okay. So for this one, it will be epsilon naught k into A. It will be K1 multiplied by A1 divided by D. Right? Epsilon naught K1 A1 divided by D. For second one, it is epsilon naught K2 A2 divided by D. Third one, epsilon naught K3 A3 divided by D. So on and so forth. Is it clear? Okay. So let us discuss charging of a capacitor. So suppose we have capacitor like this. Initially it is uncharged. There is no charge on this capacitor. And we connect this one to a battery. Connect this one to a battery like this. This is positive terminal, this is negative terminal. So slowly and slowly charge will get built up in this capacitor. Okay, so I can say initially the capacitor is uncharged, and it is connected to battery of potential difference V between the two terminals of battery. Okay, V is potential difference between two terminals of battery, terminals, sorry, two terminals of the battery, right? So now capacitor gets charged. Okay, so suppose capacitor, not suppose, it will get charged, right? So now capacitor is charging. Okay, capacitor is getting charged. So suppose Q, okay, so charge will get deposited on plates of capacitor bit by bit. So now suppose at any intermediate time capacitor is not fully charged. The charge here is plus Q, small q, charge here is, okay, minus Q. So Q is charge on the capacitor. Okay, suppose when it is not fully charged, okay, at some stage of charging. So see, here charge is minus Q, that means lot of electrons are there. Okay, now suppose some small charge minus dq emerges from negative terminal of battery and approaches here. What will happen? So this minus q and that minus dq which is coming from here, there will be repulsion between them, right? Or you can say some charge plus dq, it emerges out of the positive terminal of battery and it gets deposited on this charge, this plate, which already have some positive charge, sorry, which already has some positive charge. So the charge which is coming from this side, dq, it's coming from this side, and this charge which is already on that plate of the capacitor, there will be repulsion between them. Okay, so in order to deposit more charge, some work has to be done. Okay, some work has to be done, and who is doing that work? The battery. So it's this positive terminal of battery which is pushing this charge, okay, plus dq. Actually what happens, it will take some electrons from this side, right? So only electrons move, we know this, only electrons move. Okay, no positive charge moves because electrons are very light, only they move. Okay, they are free to move. Okay, but we can understand in this way also. Okay, electrons come from, like, electrons move like this. Okay, it is equivalent to some positive charge moving in the other way. Okay, so some positive charge gets deposited on this plate. Okay, so now what will happen? So for depositing, for storing more charge, okay, more charge dq, some work has to be done. Okay, work done will be equal to, what will be the work done? Work done will be equal to what? The potential difference multiplied by the charge. Okay, so potential difference multiplied by the charge. So then, okay, this is small work dw. Okay, and how can I write the potential difference? So potential difference, we know C is equal to what? Q upon V. So potential difference can be written as Q divided by C. But right now, how much is the charge on capacitance? How much is charge on capacitance? It's small q, right? So it is small q divided by C multiplied by the charge that you are storing in one step. Okay, it is dq. So this is the work done. Okay, right? Work done against the charge which is already present there. Okay, so therefore now suppose initial charge is 0 final charge is capital Q. So total work done by the battery, total work done by battery to charge the capacitor, to charge the capacitor, to charge capital Q. What will be the total work done? So it will be, we know it will be integral of this. Okay. So W is equal to integral of dW, which is Q dQ divided by C. Okay, integral of this from 0 to capital Q. Initial charge was 0, final charge is capital Q. So the work done is equal to, you can take 1 by C outside, integral of Q dQ from 0 to capital Q. And this is simple integral. We know it will be Q square divided by 2. So it is 1 by C multiplied by Q square divided by 2. Because, okay, upper limit is capital Q and lower is 0. It will be small q square divided by 2, and if we substitute the limits 0 to capital Q, the upper limit is capital Q, right? So it will be q square upon 2 only. Okay, so this is the work done, q square divided by 2c. Okay, so this much work gets stored as the potential energy of the capacitor. So how much would be the potential energy of the capacitor? So therefore I can say potential energy of the capacitor, it is U, we denote it by U, it is q square divided by 2c. Okay, the amount of work done is equal to the potential energy, right? So we have this one formula, U equals to half of q square upon c, or q square upon 2c. Then we know c is equal to q divided by v. Okay, so we can put that, or we can say q is equal to c times v. We can put that here. So what do we get? We get another formula, half of c square v square divided by c, and one of the c gets cancelled, so it is half of cv square. Okay, and one more formula is possible. So if you put c is equal to q upon v here, this q divided by v, so that v will go into the numerator. So another formula we get, half of q square divided by q upon v. So one of the q will get cancelled, this v will go into the numerator, so you get half of q times v. This is another formula. Okay, then one more thing, this is the total energy stored in a capacitor, right? Now let us pick any one formula. Okay, and now I want to write energy per unit volume. Energy per unit volume of the capacitor. Okay, let us see what is that. So it is U divided by volume. Okay, volume we can denote by V, but V we are using for potential difference. So U upon V, let's denote it by small u. Okay, so small u is equal to energy divided by volume. So now what is volume of the capacitor? It is area of cross section multiplied by, so see, capacitor is like a cube. Okay, you have these two plates, they have some area, a is the area, and not a cube. Okay, it's like this. Okay, so it's a cuboid. So how much would be the volume? So it is this area multiplied by this distance, right? For a cube it is this area L square multiplied by this length. Okay, So here it will be this area multiplied by d. So this is the volume. So I can say it is U upon AD. So half of Q square by C and divided by AD. Okay. What is C? So if it is an air filled capacitor, so I can say U is equal to half of Q square divided by what is C? C is epsilon naught A divided by D. Okay. So you have epsilon naught, this is C, epsilon naught A divided by D multiplied by epsilon naught A. Sorry, not epsilon naught A multiplied by D. Okay, so what happens here is this D and D gets cancelled. So we have Q square divided by A square, and we know sigma is equal to Q divided by A. Okay, so we can put sigma as Q upon A, and we get U equals to half of sigma square upon epsilon naught. Okay, this is energy per unit volume of a capacitor. This is one formula. We can get another formula. So we know E is equal to electric field is equal to what? Sigma divided by epsilon naught. So we can say sigma is equal to epsilon naught E. And if we substitute that, we get U equals to half of, instead of sigma, I will put epsilon naught E. So it is epsilon naught E square divided by epsilon naught. So that is U equals to half of epsilon naught E square. This is another formula that I get. Okay. So energy per unit volume of a capacitor is either this formula half of sigma square divided by epsilon naught, or this formula half of epsilon naught multiplied by E square. Get it?